Hello, welcome to YouTube channel scientific underscore math and welcome to this lesson solving system of linear equation using iterative method. Okay, so Jacobi iterative method we have already studied in the previous lecture. The link is available in video description. You can watch if you have not watched those lectures, then you really need to go back and watch those lectures. Link is available in video description. Okay, so in this lecture we will solve example using the Gauss-Seidel iterative method. Okay, so let's start. Solve Gauss-Seidel iterative method. Solve the following four set of linear equation using the iterative method. Okay, so we have given four system of linear equations, and we know that what is our first step. The first step is we write them in the matrix form. Okay, so we have the matrix form of this one. This system is this one, and this is the coefficient matrix. Okay, so we have a criteria for convergence for the system or the convergence for iterative method when the iterative method is converges towards the exact solution, and when the coefficient matrix is diagonally dominant or strictly diagonally dominant. Okay, so how we can check the given coefficient matrix is diagonally dominant or not. We have already studied in a lecture, that is the diagonally dominant matrix. Okay, so I will provide the link in video description. In the you can watch, and we have also write a MATLAB code for diagonally dominant matrix. Okay, so we check we check the matrix is diagonally dominant or not. So for this one, we know that for diagonally dominant, the diagonal entry or the diagonal or the pivot element should be greater than the absolute sum of the diagonal elements in that row. Okay, so here we can see that this one is the diagonal entry, and the absolute of the diagonal entry should be greater than or equal to the absolute sum of the diagonal entries in that row. So in this case we can see that 9 is a greater than 7. This mean this fulfill the criteria for first row. Similarly, we can see that this one we have the diagonal entry, and the absolute value of this one should be greater than or equal to the absolute of diagonal entries. Okay, sum of absolute values of diagonal entry. So we can see that in this case again it is greater than 7, and for this one this should be greater than the absolute values of and these of diagonal entries in that row. Similarly, this one is also greater than, and the fourth one is also greater than. This mean this system or the coefficient matrix is a diagonally dominant. Okay, so strictly diagonally dominant. Next, note that the given system satisfies the convergence criteria. It may be written in explicit form. Okay, so next step we have, after checking if the given system is diagonally dominant, then we write the system as in explicit form. Okay, how we can write them in explicit form, I will show you for the first equation, then other one also on the same step. Okay, 9x, sorry, we have 9x1 will be equal to 54.5 minus, we take all of them to right side, minus 2x2 plus 3x3 and 2x4. Okay, So in the next step, x1 is equal to this one is a multiply over here, and on the right hand side this will be divide. Okay, and 54.5 minus 2x2 plus 3x3 and plus 2x4. Okay, so this one is the explicit form for the first unknown, that is x1, similarly for x2, similarly for x3 and x4. Okay, so we have the explicit form of the system of four linear equation that we have. Okay, now we write all of them in k plus 1 form. That will be the iterative formula. Okay, so this one now we have in these four system of equations in k plus 1 form. Okay, so next we will use the initial estimated solution, and this initial estimated solution can be zero. Means x11 can be 0, x22, x12 can is equal to 0, x13 is equal to 0, and x14, all these can be 0. But I will use the initial guess or the initial values. By calculating this formula, you will see that the system will converge faster towards the exact solution as compared to these, by using these initial guess or the initial estimated solution. So I will use the initial estimated solution by using this formula, and you can use this one, and uh, compare both of them. You will see that the exact solution, the system will converge toward the exact solution faster by using these iterative estimated solution, okay, as compared to this one. So we have the estimated solution, initial solution are this one x1, this one for the x12, this one for x13, this one for x14. Okay, so now we substitute these one into the system of equations, and then we calculate the second estimated solution, third estimated solution, fourth estimated solution, until the system is converged towards the exact solution. Okay, so we have in this column we will see the iterations, in this column we will see the simplification, and in this civil column we will see the relative errors. Okay, so okay, iteration 1 for k is equal to 1, we have four system of linear equation in explicit form. We substitute the values of x12, x13 and x14 in this equation, and we will have the after simplification new estimated solution will be this one. Okay, so we can see that after substituting and simplification we get new estimated solution, that is x21, and next for okay. So what is the difference between the Gauss-Seidel method and the Jacobi method? Let's have one look. I will okay. So difference between the Jacobi and the Gauss-Seidel method is, in the Jacobi method the estimated values of the unknowns are all updated at once at the end of each iteration. But in Gauss-Seidel method, when a new estimated solution for an unknown is calculated, the value of each unknown is updated, okay, and used in the calculation of new estimated solution for rest of the unknowns in the same iteration. Okay, so this one is the major difference between the Jacobi method and the Gauss-Seidel method. I will show you the difference between the Gauss-Seidel method and the Jacobi method. I will show you how we can use the new estimated solution for the rest of the unknown to calculate the rest of the unknown. Okay, okay. So here we can see that we have calculated the new estimated solution for x21. Now we use this estimated solution to calculate the rest of the unknowns. Okay, here we can see that we have substituted this value. We have used this value instead of this one. Okay, on the same iteration. But in Jacobi method we used at the end of the iteration means in a new iteration for an iteration 2 the new estimated solution. In iteration 2 the new estimated solution. So but in Gauss-Seidel method we use the new estimated solution to calculate the rest of the unknown. Okay, here we can see that here we have used new estimated solution, and new estimated solution. So when we have calculated x21, we will see that for the rest of the unknowns we have used the new estimated solution. We have updated the previous one. This one is the previous one, x21, this one with the new estimated solution like this one. And after calculating the x13, we have updated this one with this value. We can see that this one is the x13. X1. Okay, so this is the difference between the Jacobi and the Gauss-Seidel method. Okay, so for iteration number 2, we have the fourth system of linear equation, and we substitute the values of all these unknowns x21, x22, x23, and x24. Okay, so this one, and this one. After substituting, we and simplifying, we get the new estimated solution, and now we use this new estimated solution for the rest of the to calculate the rest of the unknown. Okay, here we can see that we have used this new estimated solution in. Okay, so now after calculating the x32, we use these. We update the previous one with the new estimated solution. Okay, to calculate the rest of the unknowns like this one and this one. We can see that this one and this one. So again, now simplifying this one, and we get the new estimated solution, and we update all the previous one with the new one. So we get the new estimated solution, that is the x32, this one. Okay, so and we know that how we can calculate the relative error, previous minus the new new estimated solution divided by this one, and we will get the relative error. Okay, so next iteration number 4, we have number iteration this one, and then this is the 3 iteration. Okay, so for k is equal to 3, and these are the 4 system of linear equation, and we substitute the estimated equation x31, x32, x33, and x34 in these equations, and after simplifying it, we get the new estimated solution, that x41, and next we update the previous one with this value, and after simplifying this one, we get the values of the unknown x242, this one, and then we again update the previous one with the new one, and simply we will simplify. Okay, so again we use the new values to calculate the new rest of the unknown. Okay, so again similarly there will be 3, because we have k is equal to 3, third iteration, k is equal to 3. So we will calculate the relative error. This means x31 minus x41 minus x31. This means divided by x31 and absolute of this one. So we have this one is the x41, this one is the x31, and divided by x31, and we have the error like that, this one 0.0091. Similarly for x42 minus 32 divided by x32. Okay, and absolute of this one, and similarly for this one x43 minus x33 divided by x33, and absolute of this one. Okay, and similarly for last one, this one x44 minus x34 divided by x34, and absolute of this one. Okay, so this is the way how we can calculate the relative error. And next we do the iteration until the convergence has been obtained. The iteration is terminated or the stop until the convergence has satisfied the criteria. This one means the relative error should be less than the given tolerance. This will be maybe 0.001. Okay, so when the error is less than or equal to this one, then the number of iteration will be stopped. Okay, so let's see the convergence of the system using the entity lab. This is my software. You can download download this software. Link is available in the video description. Okay, so here we have the iterations, and we can see that after 9 iterations the system is converges toward 5 minus 2 2.5 and minus 1. And we can see that in this case we have the tolerance or the absolute error is equal to 0.001. Okay, so we can also see that the graph of the error, and we can see that on x-axis is number of iteration and on y-axis the error in the solution. Okay, so as the number of iteration is increasing, the system is converging toward the exact solution. And after 9 iteration, the error in the solution becomes 0 or 0.001. Okay, so we have the exact solution is x1 which is equal to 5, x2 which is equal to minus 2, and x3 which is equal to 2.5, and x4 is equal to minus 1. So Gauss-Seidel method converges faster than the Jacobi method and required less computer memory when the programmed. Okay, and you can download the entity lab software. The link is available in the video description. Okay, so thank you so much for watching my video. Please subscribe my channel scientific_.